Good morning, dear students. My name is Ferhan Mazher, and today is 25th of April 2021. Right now, we are studying the subject of physics. This is O-levels physics. Physics 5054 is its code. Today, we have set our hearts to solve May, June 2020. 2-2 paper. This is a theory paper, and this belongs from the zone 2. Today in this session, we will be solving the section B of this paper, the section A of this paper. I have already solved and updated in my YouTube channel. You can find it there. So let's start today's paper. So let's start today's paper. So the first question. So this is May, June 2020, 2-2 section B. Okay, so question number 10 is on your, question number 8 is on your screen. Figure 8.1 shows the circuit diagram of a temperature gauge. It contains an ammeter, a thermistor, a fixed resistor R, and a battery. So on your screen, you can see we have a battery here. Here we have a thermistor. Here we have a fixed resistor and an ammeter. So ammeter is basically reading whatever the current is coming out of the battery. Same current is going back to the battery. All of them, they are connected in series with each other. So here we have the current is measured at different temperatures, and a graph of the results is shown in the figure 8.2. Okay, so you can see that on the y-axis, we have current, and on the x-axis the temperature is given, and it's telling you how much current is flowing through the circuit at a certain temperature. So from here, if I know, for example, if the temperature is 80, I can tell what is the current flowing through. If the temperature is 90, what's the temperature? If the temperature is 90, how much the current is flowing through the circuit. So the first question, question number is 8, and it's A, and first part, question number 8, A, first part. State how the resistance of the thermistor changes with the temperature, and explain how the figure 8.2 shows this change. You see, if you look at this diagram, as the temperature is increasing, the amount of current is also increasing. So as the temperature is increasing, the amount of current is also increasing, which means that the resistance of the circuit is decreasing. The current can, how the current can be increased, the reason can only because you have there a battery, its EMF is constant. So why the current is increasing? If the voltage is has not increased of the battery, and there is a fixed resistor with it, and that fixed resistance is not changing. So why the current increase, that's only possible if the resistance of the thermistor is decreasing. So it means that as the temperature is increasing, the current is increasing, which is only possible if by the increase in the temperature, the resistance of the thermistor decreases. Then it's possible that the current will increase. So let me show you my answer. I have written this answer. This is a 2-mark question. State how the resistance of the thermistor changes with the temperature, and explain how the figure 8.2 show this change. Let me show you my answer. I have written this answer, and then we can change. Okay. So this is the question number 8, A, first pass. As the temperature is increasing, the current flowing through the thermistor increases. Current can increase only if the resistance of the thermistor decreases. EMF of the battery and the resistance of the capital R is constant. There is a fixed resistor, its resistance is not changing. So there is only one possibility, that the resistance of the thermistor is decreasing with the increase in the temperature. So that was question number 8A, first part. So let's let's check what's the marking scheme has to say. So question number 8 is showing up on your screen, and you can see question number 8A, first part. Resistance decreases as the temperature increases. Current increases and voltage constant as the temperature increases. So it's a 2-mark question, and I hope that you have understood. Okay, so let's move to the next part. The next part is showing up on your screen. It says that resistance and the current are used for the measurement of temperature. State one other physical property that is used for the measurement of the temperature. There are many other physical quantities which can be used to measure the temperature. For example, and the resistance of a conductor can also be used to make a thermometer, and we can also use the volume expansion of the mercury, that is also used to measure the temperature. We can also use the volume expansion of alcohol, and we also use the pressure of a fixed mass of a gas, that is also used to measure the temperature. So there are many physical properties which can be used to measure the temperature. So you can name any of the properties here. So let me show you what I have written. I have written here, suppose my answer here. So the question number 8, a second part, the volumetric expansion of the mercury is used to measure the temperature. Volumetric expansion of the mercury is used to measure the temperature. So let's check the marking scheme, what the marking scheme says. And here we go. Question number 8, a second part, volume of liquid or gas, expansion of solid, liquid or gas, length of solid, pressure of gas, length of biometallic strip, EMF of the thermocouple, color of the liquid crystals, or very hot objects. So these are the physical properties which are used to measure the temperature. You only have to name there one of them. Okay, so let's go to the next question. The next question is, he says that a temperature scale involves the use of fixed points. So what is meant by the ice point? Ice point is when your thermometer is in melting ice, and we believe that the melting point will be when you put the thermometer in the melting ice, the temperature will be 0 degrees centigrade. So whatever will be the level of that property at that point, we will call it the ice point. And the steam point is when you have put your thermometer in the steam of the boiling water, and the atmospheric the pressure should be there 1 atmosphere, and that's why we will say that at that the temperature at that moment will be called the steam point. So let me show you my answer, and then we will check what's the okay. So temperature at which the ice melts is called the ice point, and the temperature of the boiling water at 1 atmospheric pressure is called steam point. So let's check what's the marking scheme has to say. So suppose we go to the marking scheme, and you can see the marking scheme says that the temperature of the melting ice or the freezing water and temperature of the boiling water at the 1 atmosphere. So this is how we do this. Let's go back to the question paper. The next question is, at 80 degrees centigrade, the potential difference across the thermistor is 3.6 volt. State what is meant by the potential difference. Potential difference means that the amount of electric energy which is converted into any other form of energy when 1 coulomb charge flows through an appliance. The amount of electric energy which is converted into any other form of the energy when unit charge flows through an appliance, for example, unit charge flows through the thermistor. So that will be known as the potential difference. Let me show you the answer which I have written. Okay, so amount of electric energy converted into any other form of energy when unit charge flows through a resistor or a thermistor or an appliance. You can use any name. So let's check the marking scheme, what the marking scheme has to say. So he says the work done, energy change divided by the charge passed through a component. Component means thermistor, resistor, fan, lamp, whatever an appliance, which is using the electric energy. Okay, so then we have the next question. The next question is, calculate the resistance of the thermistor when the temperature is 80 degrees centigrade. I know the potential difference when on the thermistor, the potential difference across the thermistor is 3.6 volt. And from the graph which was given at the start of the question, at 80 degrees centigrade, I can check how much is the current flowing. And let's go back to that diagram. So here, when the temperature is 80, so check what is the reading of the. So the reading of the current will be 0.014. When the temperature is 80, the reading of the reading will be this. This is the reading. You can see 0.014 ampere will be the current flowing through it. So if you know the voltage across the thermistor and you know the current flowing through the resistor, thermistor, you can easily calculate the resistance of the thermistor. R is equals to V divided by I. R is equals to V divided by I. Let's go back to that question. So here is that question. Calculate the resistance of the thermistor when the temperature is 80 degrees centigrade. It's a 3-mark numerical, very easy numerical. So let me show you how I have done this. So let me show you how I have done. So the value of the V is 3.6 volt. That's the voltage drop across the thermistor. The amount of current flowing through the thermistor is 0.014 ampere. And this number I have got from that graph, figure 8.2. V is equals to IR and R will be equals to V divided by I. So the 3.6 divided by 0.014. So I will get the resistance when I will enter this in the calculator, it will be 257.14 ohm. So that's approximately in two significant figures, it will be 260 ohm. So the resistance of the thermistor is 260 ohm. The resistance of the thermistor will be 260 ohm. So let's check the marking scheme, what the marking scheme has to say. Okay, so the marking scheme says 260 ohm. So you can see that the resistance of the thermistor is 260 ohm. Okay, so let's move to the next question. The next question showing up on your screen. The current scale. What's the next question? It's a 2-mark question, third part. He said the electromotive force EMF of the battery is 25 volt. Calculate the resistance of the R. Okay. So let me go back to that diagram and show you how this will work. So from the battery, if the EMF of the battery is 25 volt and the thermistor is taking 3.6 volt, how much resistance will be available for this R? How much voltage, sorry, will be available for this? So 25 is the EMF, 25 volt. This is taking 3.6. So from 25 minus 3.6, and so this R will have 21.4 volt. So the voltage drop on the R will be 21.4 volt. The current flowing through the thermistor was 0.014 ampere. So the same current will be flowing through this R and the same current will be flowing through this ammeter. So if you know the current flowing through the R, that is 0.014 ampere, and you know the voltage drop across the R, that is 21.4 volt. You know the voltage drop, you know the current, you can find the resistance. R is equals to V divided by I, and very easily you can find the resistance of this fixed resistor. I have done this on a paper. Let me show you the second part also. Sorry, this is the third part. See, third part. So the EMF of the battery here is 25 volt, and the voltage taken by the thermistor is 3.6 volt. The voltage taken by the fixed resistor will be 25 minus 3.6. That will be 21.4 volt. The current flowing through the fixed resistor will be also 0.0114 ampere. So you can apply the formula V is equals to IR, R is equals to V divided by I. 21.4 divided by 0.014, and the answer will be 1528 ohm. If I will round it off to two significant figures, it will be 1500 ohm. If you check the marking scheme, there is a mistake in the marking scheme, so don't be bothered about the marking scheme. In the marking scheme, he said by mistake, he wrote here 15,000 ohm. This is not 15,000 ohm. It's only 1,500 ohm. Okay. So it will be, because here you see, here he made a mistake. He wrote 0.0014. This reading is not 0.0014. This reading is 0.1. 0.014. So let's move to the next question, and the next question will be question number. Okay, so we have the D part here. It says the current scale on the ammeter is linear using the values from the figure 8.2. A student marks the scale on the ammeter with temperature values that corresponds to the values of the current. The temperature is then read directly from the temperature scale on the ammeter. State what is meant by a sensitive thermometer. Sensitive thermometer means it shows a larger deflection for every degree change in temperature. So for a unit degree change in temperature, if the thermometer is showing a larger deflection on the ammeter or on the scale, it means a larger scale is shown in the property, whatever the property that thermometer is using, we will say that this thermometer is sensitive as compared to the one who is showing a lesser change in the property for every 1 degree centigrade change in temperature. So let me show you my answer. I have written this a 1 mark question. Let me show you what I have written as an answer. So here we go. If deflection on the ammeter is larger for 1 degree centigrade change in temperature, thermometer will be more sensitive. This more sensitive sentence means you are comparing it with another thermometer. So if there is a larger deflection on the ammeter for every degree centigrade change in temperature, so thermometer will be more sensitive. So if, let me show you the marking scheme, because this sensitivity article is little tricky. Okay, a thermometer where the quantity changes a lot per unit temperature rise, same temperature rise. Okay, so we have, I think the wording which we have used is a good word, is good wording. Okay, so let's move to the next part, and the next part is state and explain at which temperature this thermometer is most sensitive. You see, when there will be a larger change, when there will be larger current shown, when there will be larger current shown, then it is more sensitive, because larger the current produced, the larger will be the deflection on the ammeter. So at higher temperatures, you can see that the gradient, you understand this curve. This curve is an increasing curve. Its gradient is gradually increasing. At higher temperatures, the gradient of this curve is larger. It has a greater gradient or slope at higher temperature. So for every degree centigrade change, there will be a larger amount of change in the current. So there will be a larger deflection shown on the ammeter. So when the temperatures are higher, the thermometer will become more sensitive. When the temperatures are lower, the gradient of this curve is smaller. So here, for each degree change in the temperature, the current produced is not that much. So there will be less deflection on the ammeter. So the thermometer will be more sensitive at higher temperatures. I was just trying to explain you. The wording of the question is, state and explain at which temperatures this thermometer is most sensitive. The thermometer will be more sensitive at higher temperatures, because in the figure 8.2, the gradient of the graph between the current and the temperature, its gradient is larger at higher temperature. So for every degree rise in temperature, the rise in the current is larger. So there will be a larger deflection on the ammeter, which has been calibrated for measuring the temperature. So it's a 2 mark question. Let me show you my answer, and then we will go check the marking scheme. Okay, So at higher temperatures, ammeter will show larger deflection for 1 degree centigrade change in temperature. At higher temperature, the resistance of the thermistor will be lower. At higher temperature, you can also mention here that the gradient in the figure 8.2 is the larger as compared to lower temperatures. So thermometer will be more sensitive. So this was question number 8D, and second part, let's check the marking scheme, what the marking scheme has to say. And you can see the marking scheme says at higher temperatures, at high temperatures, larger change in current, meter deflection for unit temperature rise, same temperature rise, or larger gradient. So I think the description which I gave you, you can write that description in the answer. It's a 2-mark question. Hopefully you have understood. So let's move to the next question. The next question coming up on your screen is a 1-mark question. He says the temperature gauge is used to measure the temperature of our room. Suggest why the temperature obtained using the gauge is slightly higher than the actual temperature of the room. Okay, so the thermistor, its resistance is changing with the change in the temperature of the surrounding. But you see the surrounding, there is a temperature, as surrounding has a certain temperature. But when the current will be flowing through the thermistor, due to the resistance of the thermistor, the electric energy will be converted into heat energy. So the thermistor will be also producing its own heat. So you see, due to that, the temperature of the thermistor will be little more than the temperature of the surrounding. So that's why the temperature noted by the thermistor will be higher than the temperature of the actual room. Because when the electric current is flowing through the thermistor, that is converted, the electric energy is converted into heat or thermal energy. So the temperature of the thermistor is little higher than the, because it's also getting that heat and heat from the room. So the temperature which is noted by the thermistor will be more than the temperature of the room. So let's check what I have written as an answer. Okay, so let's increase the size. Okay, so here we go. So the electric energy will be converted into heat in the thermistor. So other than heat from the room, this heat will also raise the temperature of the thermistor. So the temperature noted by the thermistor will be more than the actual temperature of the room. So that was question number 8. Let's check the marking scheme of the last part. It says the heat thermal energy produced in the thermistor or resistor. So thermal energy is produced in the thermistor also because of when the current flows through the thermistor, electric energy converted into heat. So that was the question number 8. We are done with the question number 8. And now we are starting question number 9. Here we go. Figure 9.1 shows a simple relay used to switch a mains electric motor on and off. Explain why the motor switch on when the switch S is closed. Okay, so here we have a switch S, and it's the switch S has a battery, a small battery with low voltage, low current. It's so the wires are connected with this coil, and we have a core in this coil. So when you will close this switch, you see the current will flow through this coil. This coil will become an electromagnet. When this coil will become an electromagnet, it will attract this vertical portion of the iron armature towards it. So this vertical portion of the iron armature will be attracted towards right. When this will be attracted towards right, so it's pivoted here. So this horizontal portion of the iron armature, that will move upward. When this will move upward, it will lift this lower contact, and that will come in touch with the upper contact. So these two contacts will come in contact with each other. They will touch each other. So the path of the current for this motor, this second circuit, that will be completed. And this motor will switch on. So you see, when you switch on this S, this motor will also be switched on. And when you will open it, this will be no more electromagnet. This iron armature will go back. This contacts, they will be separated, and motor will be off. So this relay is being used as a switch. So the first question here is, explain why the motor switches on when the switch S is closed. I have already described you. Let me go to my answer. I have written this answer. Let me show you my answer, and then we will see. Okay. So question number 9A, first part. When the switch S is closed, current flows through the coil. It becomes electromagnet. It attracts vertical portion of iron armature towards right. Horizontal portion of iron armature moves upwards. It lifts the lower contact. Both contacts touch each other and circuit is completed for motor and main supply. So you can see that so I hope that you have understood this, and let's check the marking scheme, what the marking scheme has to say. And the marking scheme says, so the marking scheme is in front of you. So the core band becomes magnetized due to current in the coil, iron armature attracted to the core and contacts touch. So this was a 3-mark question, and I hope that you have understood. He says, explain why the core is made of the iron rather than steel. You see, here you can see when we make this coil, and in this coil we put a core. What the purpose of that core is, it makes the electromagnet stronger. We always use iron in as a core. The reason is that the iron is a soft magnetic material. When the current flows through this coil becomes an electromagnet. The iron helps to make that electromagnet stronger. Iron is a soft magnetic material. When you stop the current, when you open the switch, the iron immediately loses its magnetism. So this iron armature will be released, it will go back, the contacts will be open and the motor will stop. But if you have used a steel as a core, what will happen if the steel will also make the magnetic electromagnet stronger. But the problem with the steel is that steel is a hard magnetic material. So steel is basically hard magnetic material. So once the steel is magnetized, when you will open this switch, the steel will not lose its magnetism immediately. The steel retains its magnetic properties for a very long time. So the steel core will remain magnetized. So this iron armature will be attracted. Even you have opened the switch, this will be still attracted. These contacts will be still in contact and the motor will be still on. So you have opened the switch here as switch as you have opened, but if you are using a steel core, the motor will be not switch off. It will remain on. It's a 2-mark question. Explain why the core is made of iron rather than steel. So we have to give this comparison here. So let me show you my answer. I have written this answer. So, and then we will see. Iron is a soft magnetic material. It's easily demagnetizes once current is switched off. Steel, on the other hand, will retain its magnetism for longer time after switching off the current. So if steel is used, motor will remain on even after the switch S is off. So hopefully you have understood that what I have written. Let's check the marking scheme, what the marking scheme has to say. Here we go. The marking scheme. The marking scheme says steel is a permanent magnet or iron is a temporary magnet. With the steel core, motor stays on or contact stays closed if switch S is open. Even if the switch S is opened, if the core of the steel is used, the contacts will remain intact. It will in touch with each other. So this was question number 9A, second part. So let's start the next question. The next question is a student suggests that the motor can be turned on and off without a relay. He suggests connecting the mains to a simple switch in series with the motor. Suggests one reason why in some situations, using the relay is better. You see, for example, here in the circuit number 2, where the motor was connected, if in the second circuit the voltage is very high and the current is very large, then we do not make a switch in directly there, because it's not safe. We always use a relay, because relay is operated on a very low voltage and very small amount of current, and this will help to prevent an electric shock from the switch. So relay relay is using very low voltage and small amount of current, so its switch is safer for touch as compared to a switch which has high voltage, larger amount of current. Relay is operated on a very low voltage and very small amount of current, so its switch is very safe to touch for the human. So let's check what the marking scheme has to say. The marking scheme says that with relay, safer or switch as connected to low voltage or switch only handles low currents. So the switch of the relay is safe for direct touch by the human. And it will operate another switch which will be dealing with the high voltage and high current. So you don't have to directly touch that main circuit where we have high voltage and high current. So it's this kind of safety. So this is question number 9A, third part. So let's move to the next question. So here we have, so we have to reduce the size a little bit. Figure 9.2 shows the coil of wire wrapped around a cardboard tube. There is no core. There is an electric current in the wire in the direction shown by the arrows. On the figure 9.2, draw the pattern of the magnetic field inside and around the coil. Mark the direction of this magnetic field. This is a 4-mark question, a very easy question, but it's a 4 marks. You have to draw the magnetic field pattern here, and you have to mention that where will be the north. Okay, so of this electromagnet. So I've done this on a paper. Let me show you, and here we go. I will also explain that how this magnetic field pattern is going. Okay, so here we have that that coil. You can see the blue color, and that's the wire, that coil, and the direction of the current. So if you want to find out where will be the north, you use the right hand. So take your right hand. I'm talking about the right hand. Take your right hand and hold this coil in such a way that the curls of your finger, they are in the direction of the current. So I will hold this. You can do this with me. Hold this coil in your right hand in such a way that the curls of your fingers, they are in the direction of the current. So wherever the thumb of your right hand is pointing, there you will have the north. So the north will be here on the right side, and the south will be here. So the magnetic lines, due to this electromagnet, they will be coming out from here, and this is the south pole. So here the magnetic lines will be going in, and inside the coil, the magnetic lines will be flowing from the south to north, and outside the coil, they are going from north to south. So you can see this is how I have drawn, and by using the right hand grip rule for the solenoid or for the coil, I'm able to tell where is the north and where is the south. Hopefully you have understood this. Let's check the marking scheme, what the marking scheme has to say about this. He says that so at least 2 lines inside the coil and horizontal near center and covering at least 6 wires of the coil, correct shape of lines fanning out at the ends of the coil, at least 2 lines passing outside the coil from one end to the other, correct direction of the field lines, or at least 1 line and none wrong. Here in the On the figure, mark the north pole of the coil. That's so total 5 mark this question. We have already discussed that how you will find out where is the north. So on the right side, this will be the north. Okay. So now we are on the next question, next part, I mean. So here is the part. The supply of current to the coil is removed. The ends of the coil are connected to a sensitive ammeter as shown in the figure 9.3. Describe how a permanent magnet is used to produce a large reading on the ammeter. How you can produce current in here. So what we do, we take a magnet, a permanent magnet. We take a permanent magnet and we bring the permanent magnet, a strong permanent magnet, and we move that permanent magnet very quickly towards the coil or very quickly away from the coil. Both ways you can do this. So take a strong magnet and permanent magnet and move it very quickly towards the coil, and so automatically the current will be induced in the coil, and it will be large amount of current, and the ammeter will show a large deflection. It's a 2 mark question, and I hope that I have made my point clear. So let me show you what I have written, and then take a strong permanent magnet and move it very quickly towards the coil. So this is how a large diffraction on the ammeter will be shown. A strong magnet and move it quickly towards the coil, or move it quickly away from the coil. Once you have brought it near the coil, then you can take it away. Very good. Let's check what the marking scheme says about this. He says that move the magnet into near the coil, or move coil, move magnet, coil quickly, or move strong magnet. So you should have a strong magnet and move it quickly. Then let's move to the next part. Okay, so this is the last part of the question number 9. Explain why a current is induced in the first part. When you move a magnet towards a coil, when you move a magnet towards coil, you see its magnetic flux will be flowing through the coil. So when you will move it relative to the coil, the magnetic flux flowing through the coil, that will change. The magnetic lines of that magnet which are passing through the coil, they will change. And whenever the magnetic flux passing through a coil changes, EMF is induced in the coil. That's Faraday's law. And we call this electromagnetic induction. We call it electromagnetic induction. It's a 2 mark question. I have written this answer. Let me show you my answer, and then we will see. When the magnet is moving towards the coil, its magnetic flux passing through the coil changes. Due to changing magnetic flux, EMF is induced in the coil. This is called electromagnetic induction, Faraday's law. So EMF will be induced, and there will be a large deflection on the ammeter. So let's check the marking scheme. He says, lines of magnetic field cut the coil, or flux in the coil changes, induced EMF, voltage produced in the complete circuit. So that was, my dear students, question number 9. Today we are doing May-June 2020 2-2. And here in this session, we are attempting its section B. So we are done with the question number 9. Now let's move to the next question number 10. So here we have, okay. An oscilloscope is a device used to display waveforms. Inside the oscilloscope, a beam of electrons is emitted from a metal filament by thermonic emission. The emitted electrons are accelerated away from the filament by a potential difference of 2000 volt. State what must happen to the metal filament for thermonic emission to occur. For the thermonic emission to occur, the cathode must be heated. The filament must be heated. And let me show you my answer. Then we can go to the next part. Okay. For thermonic emission to occur, metal filament needs to be heated. So that was the question number 1A, first part. So let's go to the next part. We'll check the marking scheme later. He says, explain why the electrons accelerate away from the filament. In the CRO, we use an anode, and that anode is positively charged, and it is at a very high voltage. He said 2000 volt. So anode is positive, the electrons have negative charge on them. So the electrons which are negative, the anode which is positive and is at very high voltage. So the opposite charges, they will attract each other. So the electrons will be accelerated towards the anode. Plus the filament is negatively charged. It's like a cathode, and it also repels them. It repels them, and the anode attracts them. So that's why the electrons will be accelerated. So 1 mark question, let me show you my answer, and then we will check the marks. So electrons are negatively charged, anode at high voltage is positively charged, opposite charge is attract. So the electrons will be attracted towards the anode. Another reason is that electrons are repelled by the cathode. That filament is basically cathode, and it has negative charge, so it is also repelling the electrons. So the electrons will be accelerated towards anode. So let's check the marking scheme. What the marking scheme says. So question number 10, filament is hot or heated. That was the question number 10, A part. And question number 10, it's A, second part, attracted by a positive potential or repelled by the filament, or filament is negative. So this is the same answer which I gave. So hopefully there's no problem. So let's go to the next question. The next part is here. He says the charge on the one electron is 1.6 expo minus 19 coulomb. Calculate the maximum kinetic energy of one electron after it has been accelerated through 2000 volt, 2000 volt. So you remember the V is equals to energy divided by charge. You remember this formula? V equals to work done divided by charge. Voltage is equals to energy divided by charge. So I will use that formula and I will find out this. I've done this on a paper. Let me show you my working. Very simple, but this is a new question. Okay, oh, sorry. So question number 10, and it's A and third part showing up on your screen. Voltage is equals to energy divided by charge. So 2000 volt and charge on one electron is 1.6 expo minus 19. So energy will be equals to 2000 multiply 1.6 expo minus 19. And the final answer will be 3.2 expo minus 16 joules. 3.2 expo minus 16 joules. Hopefully you have understood. Let's check the marking scheme. What the marking scheme says, 3.2 expo minus 16 joules is the answer. So our answer is right. Okay, so the next B part, figure 10.1 is the trace on the screen of the oscilloscope. So here one division, here says the setting on the oscilloscope are 10 milliseconds per division for the x-axis and 3 volt per division for the y-axis. So on the y-axis, one square, that means 3 volt, and on the x-axis, 1 square means 10 millisecond. So have a look at this diagram carefully. Okay, so the first question coming up on your screen is he's saying that calculate the amplitude of the trace shown in the figure 10.1. We have to find out the amplitude. So here we go. Let me increase the size and I will show you how this is done. So this is the mean position. This is the mean position, and amplitude means from the mean position how high you went, or from the mean position how low you went. So you can clearly see that the trace is going 2 squares up from the mean position. Each square represents 3 volt. Each square represents 3 volt. So what we will do, there are 2 squares, so it means 1 square represents 3 volt. So the maximum amplitude is 6 volt. So the maximum amplitude is 6 volt. And you can also find out the time period of this wave. You see the wave is completed here, So check horizontally how many squares are used for the time period. 1, 2, 3, 4. So there are 4 squares used to complete one wave, and it means that the time period of the wave is 4 multiplied 10 milliseconds. So that will be 40 milliseconds. So the time period will be 40 milliseconds. So let's reduce the size so you can check the questions. Okay. So the first question was, okay, so here we have. So the first question was, what is the amplitude of the trace? I told you that it is 6 volt. And the second part is, it's a 1 mark question. Calculate the time for one oscillation. So we calculated horizontally how many squares are used for one complete wave. So there were 4, and each square represents 10 milliseconds. So 4 squares mean that 4 multiplied 10 milliseconds, that will be 40 milliseconds. So the time period of this wave is 40 milliseconds. I've done this on a paper. Let me show you my work. Okay, so next question. So the amplitude will be equals to 2 multiplied 3 volt. So that will be 6 volt. And question number 10b, second part. So the time is, there are 4 squares in a complete wave on the horizontal. So there will be 4 into 10 milliseconds. So that will be 40 milliseconds. So the time period is 40 milliseconds. So let's check the marking scheme, what the marking scheme has to say. And the marking scheme says 6 volt and 40 milliseconds. So 6 volts and 40 milliseconds. So that is the right answer. Okay, so let's go back to the question. And here we go. The trace shown in the figure 10.1 is caused by a sound. The sound travels through the air to a microphone from the place that it is made. The microphone is connected to the oscilloscope, which displays the waveform shown. Sound is a type of wave. State which type. Sound is a longitudinal wave. Sound is a longitudinal wave. It's a compressional wave. We use both the names. So then the next question is 2 mark question. He says, describe the motion of the air molecules as the sound passes through the air to the microphone. You see the molecule of the air. If the sound waves are traveling from left to right, the molecules of the air, they will vibrate about their mean positions parallel to the direction of the wave. And when the molecules of air, they will come close to each other, a compression will be formed in the air. And when the molecules will move away from each other, a rarefaction will be formed in the air. So let me show you my written answers. I have written these, I have written this answer, and let's see what I have written. Okay. Sound is a longitudinal wave, and then air molecules vibrate to and fro about their fixed position, or you can say about their mean position, and they vibrate parallel to the direction of the sound. So when the molecules, they will come close to each other, a compression will be formed, and when the molecules will move away from each other, rarefaction will be formed. So this is how the sound waves are traveling in the air. So let's check what the marking scheme has to say. So it's a longitudinal wave, 10C first part, you can see. And then he says that the oscillation described, for example, back and forth in direction of travel, or parallel, we say parallel to the sound waves. Or compression, rarefaction stated or described. So it's a 2 mark question. Hopefully the marking scheme is also in front of you. I have written also answer. You can also write a better answer. So let's move to the next part. The next part is, he says, okay. So the third part is, he says that describe and explain how the trace on the screen changes as the pitch of the sound becomes higher. The setting on the oscilloscopes are unchanged. You see pitch, when the pitch will become higher, the frequency will become higher. When the frequency will become higher, the time period of the wave will become smaller. So on the display, whatever the number of waves, for example, on the display right now, let me check how many waves are shown. So 1, 2, 2.5. So right now there are 2.5 waves on the display. And when you will produce a sound which has higher pitch, then there will be more than 2.5 waves shown on the display, because the time period when the pitch will be higher, the frequency will be higher, and when the frequency is higher, the time period will be smaller, because the time is equals to reciprocal of the frequency. T is equals to 1 by f. So if the f will go up, the time period will go down. So on the display, there will be more number of waves. Hopefully you have understood. Let's check what I have written. Then we will see. Okay. Higher pitch means higher frequency. So the time period of the wave will become shorter. So on display now, there will be more number of waves. So on the display, right now there was 2.5 waves. So now there will be more than 2.5 waves showing on the display. When the pitch will become higher, when the pitch becomes higher, the frequency becomes higher, the time period becomes smaller. So no more number of waves are shown on the display. So hopefully you have understood this this argument what we have written here. So let's move to let's check the marking scheme first, then move to the next part. So more waves seen on screen, high frequency of the sound, or more waves per second or time for one wave less. So these are the 2-mark question. He says the next question. Sorry, I was reading the marking scheme. So we are done with here. Okay, so now we are on the question number 10D part. A student investigates what happens when a diode is connected between the microphone and the oscilloscope. Figure 10.2 shows the circuit that uses. You see where we have connected a diode, and diode is such a thing. It only allows the current to flow in one direction. When the current will flow, for example, in this loop, if the current will flow clockwise, the diode will let the current flow. But when the current will try to flow in the anti-clockwise manner, in the anti-clockwise loop, the diode will not let the current flow through it. So diode only allow the current to flow in one direction. So figure 10.2 shows the circuit that he uses. Without the diode, the output from the microphone is an alternating current, and the trace is as shown in the figure 10.1 on the page 18. Describe the action of the diode on the current from the microphone. So when describe the action of the diode on the current from the microphone. So you see it's a 1-mark question. So diode will let the current flow in one direction only. So what will happen, because the alternating current is provided to the alternating current is coming. So during the half wave of during the half cycle of the current will flow, and in the next half, when the direction of the current will be not suitable or opposite to the diode, the current will not flow. So in a complete cycle of the alternating current, during the half cycle, the current will be flowing, reaching the oscilloscope, and during the next half cycle, the current will not be reaching the oscilloscope. So I will read this answer, and then we will see what is the. Okay. So here we have that answer. It will allow current to flow only in one direction. It will allow current to flow only in one direction. So let's check the marking scheme. What the marking scheme says. Diode passes current in only one direction, or current only flows for half the cycle. Oscillation or current is DC or direct. Now the current which you provided to the oscilloscope, that will be like DC current, because it's only flowing in one direction. So the next question is on the grid. He says, on the grid, figure 10.3, sketch the trace seen on the screen when the diode is used. When you use the diode, during the half cycle of there will be a trace which will go up, and then during the half cycle there will be no wave, and then again half there will be a wave. Let me show you. I have drawn this. Okay, so let me put this. So during half cycle of that AC current, the current will reach the oscilloscope, so a trace will be shown. And when the direction of the current, the next half cycle will be negative, so diode will not let it flow. So the trace will become flat on the mean position, then again, and then flat, and then again. So this is the display which will be shown on the oscilloscope when you are using a diode here. So I think let's check the marking scheme, and let's see what the marking scheme has to say. He says at least one top half and no bottom half, or one bottom half and no top half. We have used the top half. 3 top halves of the wave and flat section along midline, or 2 bottom halves of the wave and flat sections along the midline. We have made it perfect. So so I think the paper is over. So my dear students, today we have done October, November 2000. No, sorry, I said October, November. Today we have done May, June 2020 2 paper, and this paper belongs from the zone 2, and we have done the section B of this paper today. The section A of this paper, we have already done. We have uploaded in the YouTube, my YouTube channel. You can find it there. So I hope that you are able to understand the concepts which I have tried to explain. And this video, I hope, is very helpful to you. If you are watching it, especially if you have the hard copy of this paper, then this video will be very useful to you if you are writing this the answers there and checking it with the marking scheme. But if you are just watching this video, even this will be very beneficial to you. If this video is beneficial to you, it's making your life easier. Don't forget to subscribe to my YouTube channel, and also suggest these videos to your friends. You see, and don't forget to like my videos. And if you have any comment, feel free to comment on my video. And you see, your response is energy for me. So I hope that I have, I will be able to influence. I will be able to make some of the students around the world their life easier. So thank you very much, everybody, and keep studying and keep struggling. Thank you very much, and have a good day. God bless you all.